hopefully they can all hear me.
Is there a chat then?
That's a good point. We need to active the chat. So if you click on more, then you will see the chat box coming up.
Oh yeah. Yeah. So you can, you can chat to everyone.
Yeah, at least keep an eye on what's happening with the chats. If people have any questions or.
Oh, there's a chat already. Hi. Oh, that's Elijah.
Hello.
I'm just gonna go quickly to the bathroom. But if you want to start,
yeah. Hi everyone. It's 11:59. Please let me know if you are not hearing my voice, if there is any issues with seeing the screen. Hello everyone. I hope there is no connection issue. Okay, let's start. Hello everyone, my name is Soroor. Thank you so much for coming along remotely, of course. This is our first experience of running online seminars. So we'll see how we go. If you don't mind, so everyone can hear me well? If someone can please not, yeah, good, thank you. Yeah, I think we start just to make sure we finish on time. So today we'll be talking about non-parametric and semi-parametric models in R. And this is brought to you by RLadies Melbourne, of course. So this is a start of the very new RStat launch seminars. The focus in this series is going to be more on theoretical statistical education as opposed to doing computational. So what we have been doing so far has been mostly around coding, but we are more interested to build up your statistical knowledge. So the sessions will be 45 to 50 minutes. Potentially during, they will remain to be in lunch times. And we will be potentially covering statistics and statistical learning models. So it's really the focus is in enhancing the statistical knowledge of the RLadies community. There is a chat box. If you have any questions, I appreciate if you could type in your questions just to reduce and keep your audio at the mute state. So that we are reducing the noise level from the background. And let me know if I am going too fast. Right. So I would like to start with some reviewing some of the recent achievements of RLadies Melbourne members. So Errol Wang who presented a workshop on making R packages, was recently awarded the 2018 American Statistical Association Statistical Graphics Student Paper Award. So congratulations, Errol. And our very own Alex Garnham, who keeps posting our meetups, our events on meetups, recently was awarded the 2018 Abacus Professional Bioinformatician Award. Cool, and I think we can probably start going into the main topic. So in context of parametric models, say linear models, there's typically a very strong assumption, a distributional assumption on fitting these linear models. That includes, for example, the normality assumption, lots of hypothesis testing, and lots of the inference methods are asymptotic. There's lots of asymptotic assumptions around these methods. And so this makes these statistical models less flexible in a way that in terms of applying these kind of methods to situations where the underlying distribution assumption may not necessarily hold, or the asymptotic properties may not necessarily hold. So, but when it comes to, in context of non-parametric modeling, we typically make no assumption about the underlying distribution of the data. And the models are more flexible, they can be adapted or generalized into other cases, other modeling situations, or other data types with any kind of distributional assumption. But that, of course, has a trade-off. These kind of models are going to be more complex. They involve estimation of a large number of parameters, which is known as model complexity. And as mentioned, the parametric models are generalizable because the model is simpler, versus a non-parametric model is mostly fine-tuned. We'll get to this, but it's kind of fine-tuned to the specific problem. And so when you start to apply it in another data set, you get a larger variance for your estimate. And this is what the whole concept of Biasvariance trade-off comes about. In context of parametric modeling, the bias is typically small. The bias is large, sorry, and the variance is small, meaning that, let's see if I can figure out how to, not that. So I'm just trying to share a whiteboard. So I annotate and draw for you. Okay, I don't think this will necessarily work. So for example, if these are my data points, there's definitely a better way of doing this, but so assume that these are perfect circles. One way to fit a model is just to do a straight line. Let's assume this is a straight line. So this is your parametric model. Perhaps the other way, so let's go with a different color. Perhaps another model that will work similarly is like a polynomial fit. This would also work. So your green line is more generalizable because it's less tuned to your data. And so typically the estimates that come from this green line or your parametric methods, they don't, the bias, which is the difference between the expected value of your estimate and the true estimate, is typically large, but the model is adaptable, so the variance is small. Whereas if you take this red fit and you apply it in another data set, the point that your estimate point, like this local minimum, will still be very close to the true value, so the bias is small. However, the variance of the estimate will be large, just because in other data set you might have points that are positioned in a different direction, or they have different spread. So this is like a very general idea, and I hope I was able to cover the main point that I was trying to make. Okay, I need to quickly potentially save and go to the mouse. Okay, right, going back to the slides.
There's a question. Non-linear models and non-parametric.
Non-linear models are non-parametric. That's true. So generally, for when your data becomes non-linear, you start to apply models that are more flexible, which means that you would go for non-parametric, the models that do not rely on distribution and assumption of the data. And yes, you would go with non-parametric models. All good?
Is it? Oh, should I ask the question then? If I want to ask a question, or
if you could remind me that there's a question, thank you.
Oh yes. No, because I have a question as well. So maybe
they
can hear me.
Yep.
I can't remember. So you said non-linear models and non-parametric, but
non-linear data. If you have a non-linear data, then a linear method.
Wait. So if you have a non-linear relationship between two variables, not linear data, I guess. So if you have a non-linear relationship, unless you because there are a lot of models that you try, for example, to take the log. You have log linear, you have binomials, you have not binomials, but like you have models in which you maybe use a link function to your data to make the relationship between the two variables linear. So that you can use a linear predictor to actually estimate.
Which I have good examples of that as well towards the end of the talk.
Yeah.
So it will be covered.
Okay.
Yes, there are situations where we assume that a function of the data is linearly separable, which is defined in context of generalized linear models, which we will also be touching. And at the end, in context of non-parametric modeling. So, okay, these stay where they were, that's fine. There are two topics in context of non-parametric estimation. We can do non-parametric density estimation, or we can do non-parametric regression. So in terms of density estimation, histograms are a very typical tools that everyone has been using. It's an obvious tool to approximate the density or the distribution of a data set with a histogram. This is an example of non-parametric. You essentially just take bins or divide your data point into bins, and then you count the frequency of your data point in each bin or each interval. Then that becomes an approximation to the density distribution of your data. The other method is kernel density estimator, and it's defined by this formula, which is essentially, so K is your kernel function, and we will go through the examples of kernel function. H is your bin-width, so still we are borrowing some idea from histogram. We are still dividing our data points into bins of with H, but we are waiting. Well, what is actually happening is that for any single data point in our data set, we are assuming that we are saying that let's fix that data point, and let's for a certain let's consider a neighborhood of that value centered at my data point, where the bin where the width is just the H, or well, you have H here and then H here, so it's just 2 of H. So essentially, it's a local sum. It's a weighting of the sums of. So you move towards every single data point in your data set, and you start to consider a neighborhood around that, and you sum all these up, and you'll get an estimate of. So if this is your true density, the sum of these bumps should give you a kernel density estimation. the idea is to consider a neighborhood and come up with some, or choose some mappings that converts for making a distribution around that for that neighborhood centered at your data point. So some of the choices for kernel function is, for example, you can take a uniform distribution. So essentially, a kernel is just a function times by the indicator of the support of that kernel. So for example, I'm saying that take all the values that are within this interval and then do different transformation. It's some kind of transformation times by that indicator function. That indicator function limits, it's the support of your vector, and that limits the operation, the transformation that you are doing to that specific interval. So this is, for example, is saying that for every single point from here, for example, for between -2 and 1, if the absolute value of the data point is less than 1, then do this transformation on the data point. If not, then return 0. So this kernel approximation that you are saying here is definitely a Gaussian approximation. All good? Everyone happy to move? Yeah. Feel free to just to clarify. Both HIST and KDE are to bin and smooth your data to see distributions. That's right, yes. The difference is that a histogram is not a weighted approach. Every single point has an equal weight of 1/n, but for a KDE, in context of KDE, every single point has a weight that's determined by the kernel value. All good? So really, KDE is a weighted way of doing a histogram. So that when you have higher weights where the points are closer, you have less weights if the point is like there is no point within the vicinity of the data point you have fixed, and so on and so forth. Is the uniform kernel the same as the histogram then? No, because a uniform means that, let's go back to the annotation. Annotate, let's pick a blue color. So for a uniform kernel, if this is your fixed point, a uniform kernel takes, well, this value is definitely, so a uniform kernel requires, okay, I'll need to go back to notes. So this is a definition of a uniform kernel. It says that return half for the values that are between 0 and between 1 and -1, right? So what it does, it says that is this point, it says that is this point between between -1 and 1? Yes. Then return, then assign this half, which is here, right? So essentially it says that around this point, the mass is half in here and it drops to 0. But this depends on the h that you consider, right? So for example, if my h is between here to here, right, it says that anything out of this h has to go to 0.
So is it like it gives the same weights to all the points in the intervals, whereas with the Gaussian kernel, you actually weight less things that are, so because all of these things are done for everything. It's a
more sharp weighting of things.
So if you want to give an estimate of that point that you click with the center of the, the interval, if you use the Gaussian one, you will have
this
different weights. So
yes, that's
decreasing weights as you go around, as you go away from that center.
That's
so
right.
Whereas that one will be the same.
Versus this one goes. So if the H, for example, is roughly over there, it goes down to 0 very sharply after that H, after the this entire. Okay, got it. Good.
There's another question. Oh, got it.
So,
can I ask the last question?
Yes.
So, because if you can you change the slides to all the kernel densities, the kernel functions. So that is, for example, most of the functions are for if U is in between the -1 and 1.
Yes, most of them have a support between.
So what happens if you want to smooth, like for example, the function that you wanted to smooth there had values that were outside of those boundaries?
So it retains 0.
It will just not smooth things that are outside of those boundaries.
So note that this is really a sliding thing, right? So for this point, it considers a kernel, then it moves to the other one, right?
Yeah, when it goes to...
Yes, so the point where you think is actually 0, it's like estimated by the next point, it's like covered by the next point.
Mm-hmm. So in a sense, you can, I remember doing this, but maybe I don't remember that it was support, so maybe you need to be careful of what function you're trying to smooth and use as different kernel, because I remember kernel were not that important. The kernel is important, but not that important when you're trying to smooth the function.
Yes, and I think the one of the books that I'm going to introduce at the end has different photos. I don't have it here. I actually might be able to bring it up to look it up. So let me see.
Anyway, I don't want to get distracted too much, but
so these are different kernels, if everyone can see. I hope they can see.
No, I can't see them. Because maybe you have to share. Yeah. If you do share, you have to share up there.
You have to change the sharing.
Below all the people. No. Oh, yeah.
Minimize. Okay, that's good.
You share. And you can share the whole desktop so that everything that you see, they see all the things.
I think it's safe to.
Okay.
So this is, for example, trying different kernels. This is an example of a quadratic kernel versus compared to a uniform kernel, compared to a Panathinaikov kernel and a triweight kernel. So some of the kernels the transformation is more similar, or the estimate of the density is more similar. Some of them are less similar. So for example, these two are definitely considerably different compared to quadratic and uniform kernel. Yeah. Let's go back to.
Is it this way?
Okay. I think everyone is happy. So that was estimation, very quickly, estimation of density. Now we are interested in regression. So as we mentioned, we are making absolutely no assumption about the underlying distribution of data. As a result, we model the response, which in this case is y, as the conditional mean of x, your data point, the observed data point. So we are always dealing with conditional mean or conditional expectation of the response. This is actually what we are trying to do. We are trying to find the best m of xi given that this typically has a normal distribution. This is your error term, and your error term typically has a normal distribution, 0, standard deviation 1. Y is your response, which you don't know what distribution it's coming from, and you are hoping a fit, or in terms of conditional expectation, that could model your response. So this is what we are going to. We are hoping to find that we are going to cover different ways of estimating NXI. So the first one is called an NW estimator. Because the next topic is called the local polynomial regression, it's important to know that an NW estimator is just zero-order polynomial regression, or also called a local constant regression. Your estimate of M hat is again a weighted sum of your response, and it's given by that formula. So this assumes that, again, K is your kernel density, and again, you are considering a neighborhood around centered at your X. Y is your response, and then this gives you an estimate. Well, these both give you an estimate of your M hat or your conditional mean. And note that this whole slightly scary expression can be written as some W, essentially some weights of Y, that 1 over N sum of weighted Y. It's just a weighted average of the observed of the response. So this is what an NW estimator does. It's a weighted local average of the response. And if you have, for example, a net income, if you have two variables, net income versus food, fitting an NW estimator is essentially fitting a curve or a smooth, which is a local, which at any given, which is essentially an average of a locally weighted, it's a locally weighted average of the response. Okay. However, so if you are if the data is really if data is either really nonlinear or well, as Anna mentioned, the relationship between the response and the covariate that we are interested to consider to investigate is nonlinear, perhaps it's probably more appropriate to do a local polynomial regression. What in the context of local polynomial regression, the aim is to find these coefficients beta 0, beta 1 to beta p, similar to linear model, such that these polynomial orders of observed data points around a fixed center that we consider, it minimizes that expression. So the estimates for beta that minimizes this loss. So let's go with the drawing mode again. Sorry about the inconvenience. So we would like to find the values of beta that minimize that expression, which is essentially so this is a power 1, this is a power p. It's just a polynomial power of different powers of or polynomial order of your data points centered around some fixed values, and you would like to minimize this expression from here, the distance of that with respect to from the response, and again weight it by a likelihood of by the neighborhood, by a local, by doing a local weighting, right? So it turns out that the solution to this minimization problem is very similar to a weighted least square. So the formula is different. Your X matrix is not your simple design metrics in context of a linear model. It's actually a matrix of these values of the xi minus x for all the observations to xi minus xp. And the local polynomial estimator is actually only the first component of this beta hat. So it's just these unit vector. By unit, I just mean that the first is 0. Sorry, the first is 1. The first number is, or the first integer is 1, and the rest of them are 0. So you're doing only the first component of this is your local polynomial regression, i.e. your estimate of m hat. So far, so good. So apart from the, in addition to the local polynomials, we have this, we have these splines. So for this, so note that for the previous case, if you want to estimate a local polynomial regression, note that we have to estimate p different parameters, and depending on how far we want to go with that p, increasing the order of the polynomial, that can mean a lot of number of parameters to estimate. So it just increases the complexity of the model. So splines or splines, they essentially what they say is that let's take your data point, and instead of binning them, let's fix some of the data points. We fix these data, we call these fixed data points and knots as knots, and we start to fit piecewise polynomials that was just covered between these knots. A very famous spline is a cubic spline, which is an order 4 spline. And essentially what we are doing is that we are saying that if, for example, I have a single covariate in my data set, so I have my response and I have a single covariate, then my design matrix should have the intercept term, x, the covariate itself, the squared of x, and then all the way to order L minus 1. It should also have the difference of my coordinate minus this epsilon 1 to epsilon j. These are your knots. So you have, in this case, you are fixing j knots, and so you're doing okay all the powers that I can get from my covariate plus the difference between x and knots raised to the power of L minus 1. L being the degree of your polynomial. So these are called as truncated power series bases, but they are found to be numerically unstable, and so B-splines is more preferred. And I would like to refer you to the reference textbooks, which I have one of them at the end of the slides if you're interested to read more about these plans. All good. This is a representation of what's happening with the splines. Again, you're partitioning your data. So here, for example, would be your knots. So your data is really a nonlinear format, right? You have points that you can fit a curve to it. And what you are doing is you are partitioning your data. You are taking, this is my one, this is my knots 1, this is knot 2. You are fitting in context of constant local regression or the NW estimator. What happens is that you fit a straight line, sorry, a constant line between, you know, the support of the data and the first knot, then again you fit another constant line to between the knots, and so on and so forth. When you have for a local linear polynomial, this is when polynomial has order 1. So a local constant regression, or the NW estimator, is the polynomial order 0. A local linear estimator is just a polynomial local linear estimator with order 1. And this thing here is just considering that it's just making, see how there are discontinuities. This is not really good for approximations. When we approximate densities or fits, we don't want discontinuity. So this is saying that if you try to make this continuous, then you are closer to get a spline.
Sorry, you are closer
to get a spline.
Spline is if you try to do a lot of discontinuous things, probably you should just try a spline.
Exactly. So this is where the topic of smoothing splines come into place, where you could go constant, you could go linear, but eventually for a perfect approximation or for a perfect fit, it has to be continuous. So how do you control that continuity? The idea is that, again, your aim is to find an approximation. This is your smooth or your spline. You want to minimize the distance between, or the sum of the square errors. This is the sum of the square errors between the observed value and the estimate you're using. But at the same time, you are saying that that smooth has to be continuous, and that continuity is determined by the second order derivative of g of x. And this lambda just tells you whether you want this to be like that, or you want to be like this, and potentially even get smoother until it approaches the blue line. So the advantage with this is that we don't have to select manually the number of knots. The number of knots is essentially every distinct data point becomes a knot. And you have a control over deciding the curvature of how well you want the approximation to the data be, in terms of like the curvature of the fit to be. And so the solution to that, so this is essentially a polynomial. It has, again, the beta values, the beta hat, the estimation of beta hat, the formula is calculated in this way, which is very similar to a ridge regression. And then your g hat, estimation of g hat. Okay, so what we are doing, sorry, I correct myself. What we are doing is that we try to find basis, right? Because we said that splines are actually basis, right? So we're trying to find beta hat estimates for any of these single terms in here. So this is the coefficient of this would be beta naught, beta 1, beta 2, so on and so forth, right? So we need to find the coefficients, the beta values that minimize the sum of the squares, which is this one. So once we found those beta estimates, then the sum of those times by the basis, this is your basis, gives you an estimate of your g hat, which is the minimizer of sum of the square residuals, or the distance between the estimated fit and the observed fit. All good? Any questions so far? Okay. As we said, there are heaps, these non-parametric models, particularly splines, or even polynomials, local polynomial estimates, typically require a very large number of parameters to be estimated And in a very high dimensional, we covered so far the one-dimensional situations. So imagine as the dimension increases, you even have to estimate more and more parameters. And this will have an issue of case of dimensionality. The model eventually will become very complex. It becomes less generalizable or adaptable to another situations. So one of the solutions is to use a combination of parametric and non-parametric models, just to reduce, just to avoid estimation of a large number of parameters. And this is where we have the semi-parametric models. Essentially, semi-parametric means that we are having part of the model is parametric. It relies on some distributional assumption of the data, versus some part of the model is not making any assumptions about the distribution of the data. So some of the models include additive models. Again, MX is your conditional mean. You're trying to estimate conditional mean. So in additive models, so D is then your dimension, or the number of variables that you have in your data. The idea is that you can, you fit a spline, for example, a G, a nonlinear function, to every single D dimension. So you have sum of nonlinear fits. In a partial linear model, you are again modeling the conditional expectation, but you are saying that I have a part that is similar to a linear model. So this is your X transpose, your typical X transpose beta in context of a linear model, plus some nonlinear part. So all the nonlinear parts are shown as G of something. In the generalized partial linear model context, you are saying that that expectation, that mean is some function G of a linear part and a nonlinear part. And this function is typically, so in context of generalized linear models, this is called the link function, and for the link function is known. So for example, when you have a log link, you assume that the log of your expected value is U transpose beta plus G of T. So assuming some function of your mean can be modeled by a partial linear model. So that's the other way, an equivalence way of saying that. A generalized additive model is similar to the additive model, apart from the fact that you again think that some function of mx is giving you the sum of nonlinear functions. And in single index models, this link function is not known, and it has to be estimated. That is the difference. So we are done with covering the theories.
Sorry, I couldn't type quick enough.
I'll go through the data analysis example that I've tried to put together for this talk. This is the Parkinson telemonitoring data set. What it essentially doing is taking observations, it's measuring recording. So it's taking observations from recording the voice, taking some voice measurements from people with Parkinson at different Parkinson developmental stage. And it's doing many different measurements. Some of the measurements are linear, like jitter and shimmer. This is just a toy. It's not a toy example. It's a real data set, but I think that yes, one question. Sorry, wasn't clear the difference between the generalized additive model and generalized partial linear. So, thank you for the question. The generalized both involve a link function. The only difference is that in the generalized partial linear models, you have a linear term and a non-linear term. Whereas in the additive models, you again have this link function, but you only have a sum of non-linear functions. I have an R code, an example from the mgcv package on the telemonitoring, the Parkinson telemonitoring data. So that may help in distinguishing between a partial linear model and an additive model. So a partial linear model, of course, it's partial, partially linear, partially nonlinear. An additive model is just sum of nonlinear functions, nonlinear fits, or what we call it a smooth. All good. You're welcome. So with Parkinson, we have some responses that are taking response variables, and they are having some nonlinear terms and some linear terms. And we would like to model the data set. So first of all, we can do some and I know it's it's potentially very hard to see, and I didn't manage to find a good way of embedding all the code in this context. But so let's go through. Let's start from KDE, or kernel density estimation. So on the y-axis, we have one of the responses. X-axis, another response. We had two response variables and many more covariates or exploratory variables. And you see that if you fit a two-dimensional KDE, this, for example, shows you that you expect a very linear relationship between the two responses, or a correlation, a very good correlation between the two responses. Whereas this one is plotting one of the responses with respect to age, right? So you start to get a feeling when you do a non-parametric kernel, when you do a kernel density estimation, you start to get for a feeling for the shape of the relationships, really. So this is saying that, like, you typically have all the masses are for the very small values of shimmer. Same here, that's the jitter. That's the jitter exploratory random variable versus that one. Right. So you start to get the feeling that the general idea is that this kind of this is a way of kernel doing a multi-dimensional kernel density estimation, and it can tell you something about the relationships. The mass, where are you more likely to see more masses? Where are you likely to see less masses of data point? So this is an example of a kernel regression, or the NW estimator. For the NW estimator, of course, you need to provide it with a going back to the previous slide, contour and KDE2D is really the functions that you need, and then you plug in your response and your variable of interest here to make a two-dimensional kernel density plot. I think that's in the base R. So for an NW estimator, you of course need to find an optimal H. The optimal H is typically determined by doing one leave-out cross validation. So in this case, we are using a custom script to come up with the optimized H, the beamwidth value, the value for the beamwidth. But the idea is that you can use kth, moose, and plots to make an NW, to fit an NW estimator to a data. So here we are taking our nonlinear terms and plotting them with respect to one of the responses, and we are fitting an NW estimator. So you get a feeling of, this is essentially a curve to the data. But it's a very simple curve in a way that we have no options on making this estimate or this fit smoother or smoother. So the main part is really, I push this over here. We want to, but as we said, so we have two responses, several other covariates. Some of the covariates are linear, some of them are nonlinear. How do we know some of them are nonlinear? We are given in the description of the data set that some of them are not linear, right? So we are relying on the information that we are given. So it makes sense to use a partial linear model, right? Because we know that some of the terms are linear terms, and we know that some of them are nonlinear terms. So the GAM function in the mgcv package enables to fit these generalized linear models. For this data set, we are using a Gaussian link function so we are assuming that the data have no specific link function. We are not doing a log trans. We are not, for example, we are not fitting a log linear model. So we are assuming that that G is identical. It's the identity link. We are and also of course on top of that, we are assuming that Y is Gaussian, but we don't know the relationship between Y and the covariance. We are not making any assumptions on the relationship between Y and covariance, which is the thing that we try to model. The model consists of fit for linear covariates and some regression splines denoted by S for nonlinear terms. And of course, this is an extension to the generalized partial linear models. Why do I say it's an extension and it's not the generalized partial linear model? Because the partial linear model is saying that you can have a linear part, X transpose beta times, X transpose beta, plus one G of X, so one of these S's, one smoothing spline or a regression spline, whereas here we have two terms that are actually nonlinear. So we are saying that I want a regression spline as a function of the PPE variable, and so we have more than one nonlinear term. These are all linear terms, so I hope you appreciate that this bit is actually very identical to fitting a typical linear model. And this S just indicates that we are interested in a nonlinear in fitting splines or a nonlinear relationship between the PPE and motor UPDRS. And of course, because we are working on patient data, we know that we expect some of the we expect the observations coming from one single subject to be more correlated compared to observations or measurements or records from different patients or different individuals or different subjects. So we are using this term, this notation is fitting an spline, but it's a random effect term. It's including the subject as a random effect term into the GAM model. So it's a way of addressing random effects, incorporating random effect terms into the generalized additive model. So just to clarify, if I had this bit, the linear parts, and a single, and just a single term, I would have a partial linear model. Because I have more than one nonlinear term, that's now a generalized version of a partial linear model. Right? That's where the additive model comes from. Because recall that in additive, we just have summation of multiple nonlinear terms. So that's where it is coming from. So you can do summary fit as per the linear models, and you will get estimates for the parametric coefficients. So here it tells you that I'm assuming that my response has a normal distribution. The link function, I'm using an identity link function. I get estimates for the coefficients for the linear coefficients. And I get an estimate for the smooth terms that are fitted for PPE and RPDE. And of course, like this is the estimation of my random effect term.
So, can I ask one question?
Yeah.
So is it like if you didn't include the
random effect?
Not the random effect, but those are the estimate of the variances. No, these are not the estimate.
You get estimate.
I was wondering, yeah, if you didn't include those non-linear terms, then you could just fit a normal linear model.
Yes,
right?
You could, yeah.
And is that equivalent, like the top part of this thing is equivalent to just fitting a linear model? Because I'm assuming identity and coefficient.
My understanding is that when you specify it as a partial linear model, it first estimates the linear part and takes the residual and estimates the splines from the residual of this.
Okay.
Whereas if you treat the whole thing as a linear model.
Like, for example, because you could, in theory, include splines within a linear model. Like, could you do the same thing? For example, if instead of using GAN as a function, I write Ln, let's say I'm a linear model, but I still include splines for my predictors. So just can you do that? And then
I think in LM does not recognize the S term, because the only way
maybe there are other ways of fitting splines.
I am not sure, honestly, whether LM can take nonlinear terms, because LM just stands for linear models. And the only way to really have those likelihood estimation. Well, that's right. So here we are using the RAML estimate. So we are getting, there are different options, there are different ways that we can choose to calculate the likelihood. RAML is one. I think there are a couple more options in mgcv. I think the best way is to refer to mgcv vignettes to learn more about how does the estimation happen, and what kind of different approaches are used to calculate the deviance and likelihood. Yeah. Cool. So the other thing that I would like to point out is the MP package. MP, of course, stands for non-parametric, and this package has very cool functions, essentially. But one of the things that I really like is making that 3D shapes of, so it plots your response against any of the co-rays that you choose, and it makes 3D plots so that you can, so what these 3D plots, they measure the density. So again, you could see, for example, that the likelihood or the interaction of these two variables is higher for DFA values that are in range 0.8, and for the motor UPDRS values that are like 30. So you see where that likelihood function is, well, the likelihood between these two variables, or the joint density between these two variables has a is maximized, right? So you're able to find those local maximums, see them.
So is this not a third variable? So in theory,
this is the density
you could see with colors, like in 2D, but with colors.
That's right. Yeah. So this is like the joint density of your two variables. So I thought I show them to you because when it comes to showing interactions, one of the best ways to show that two random variables are really interacting, but in a nonlinear context, is using this kind of 3D plots, because you are able to see the joint density of the two things, and you can see that the joint density is more likely to be higher for certain values, which is really the interaction, right? The context of interaction. Speaking of interactions, in a linear model, we would specify interactions by stars, for example, between x1 star x2, whereas for finding the interaction between nonlinear terms, we use tensor product splines, or tensor product smooth. And the way to specify that you are interested in testing whether two nonlinear terms interact is to including a term by TE. So TE bracket and then your two random variable. And of course you can change the likelihood estimation method that you're using. So that's a nice way of looking at the interaction between nonlinear terms and to see if the interactions are significant or not. That was it. It's slightly late, more than 45 minutes, but even 50 minutes. But I would. So the figures and definitions in this presentation are coming from Leo Halpin's material. The Parkinson telemarketing data analysis was a joint work of Gabrielle and myself. I really like the, well, this is the textbook that I think is potentially one of the best textbooks, reference textbooks for generalized additive models. I hope you appreciated that the GAM models and the mgcv package is really flexible. It's really a great package. Lots of potentials for someone who is dealing with data sets that could be modeled using these kind of non-parametric, semi-parametric models. I really like this article by John Racing, and I highly recommend it as an introduction. This is really a not introduction, theoretical introduction. It assumes that you have some information, you have some background on semi-parametric, non-parametric modeling, essentially what we covered today. That should enable you to go through and easily read that article. This is more about how to fit different models, including single and index models that I didn't manage to cover in R. So I really highly recommend it. And of course, the mgcv package vignette. And I'm sure there are plenty other resources that I did not have a chance, or I haven't come across, or I haven't had a chance to go through. So this was the very first RStat online session, but RLadies Melbourne will soon experience substantial structural change, and your feedback is important in deciding whether we need to keep these RStat online sessions, or you think, no, there's probably no advantage. So there's a Google survey. There are only 4 questions. I will need to, yes, I should potentially, I can copy this to...
You can put it in the chat.
Yes,
right.
to the chat.
Yeah, because then we can, yeah.
Cool. Let me know if you have any problem accessing the Google survey. That was it. If I'm happy to stay in, I only have 8% charge, as if like battery charge. I'm happy to stay a bit longer. If you have any questions, feel free to unmute and ask, or send me an email later. That's it. Thank you, everyone. And I'll take questions.
Thank you very much.
Thank you, sir.
Thank you for everyone who came along. Yeah, thank you.
Okay, I'm going to go to the dentist. Oh.